Alright, today we're going to continue talking about parametric relations and inverses. How to find an inverse function algebraically. You're going to rewrite f of x using y, then you're going to switch x and y, that's what makes it an inverse, and then you're going to get y alone again, rewrite it in function notation, and then restate any restrictions on the domain of the inverse. How to find the domain of the inverse of a function. Find the domain of f of x. Okay, sketch a graph of it, find the domain of the inverse, sketch a graph of it, and decide if it inherits any restrictions from f of x. Alright, so it says find the inverse of this function. Notice that there's no drama. So right now, the domain of f is negative infinity to infinity. There's no drama. Alright, to find my inverse, the first thing you do is you switch this to y. The next thing you do is you switch x and y. So y becomes x and x becomes y. And then I have to solve it for y. So to get y alone, I'm going to add 6. That gives me x plus 6 equals 3y. Divide by 3, divide by 3, divide by 3. I get y equals 1/3 x plus 2. You can't use that notation because you can't claim that y equals two different things. What we're really finding is y prime, or the inverse of y. So what you do is you just replace it with the inverse of function of x is 1/3 x plus 2. And you can see by my inverse function there's still no drama. Yeah, I have a fraction, but there's no letter in the denominator. So no drama means that my ultimate domain is negative infinity to infinity. Okay? Oh, sorry, I told you the steps there. And apparently if you graph it, oh, I know what I was going to show you, yeah. We're not to this point yet. I'm kind of cheating and getting a little bit ahead. There's one way you can check to see if you did your math right. The graphs of inverse functions have to either intersect. You see where the two lines intersect? Here's my 3x minus 6. Here's my 1/3 x plus 2. They intersect right there. That line in the middle is the mother function. It's called the identity function. We talked about it, right, in 1.3. There's the identity function y equal x. We call that the mother function of everything. Okay, the identity function. And you see how it intersects where they intersect. That's the telltale sign that you have inverses. If your mother intersects where they intersect, those two are inverse functions to each other. They don't have to intersect. I'll show you another one where they're also inverses without intersecting, but this is a telltale sign that they are inverses. Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got 4. Alright, so I changed this to y. Then I'm going to switch x and y. So x equals 5y plus 6. Then I'm going to get y alone. So minus 6 minus 6. X minus 6 equals 5y. Divide by 5. Divide by 5. Divide by 5. And I'd get y equals 1/5 x minus 6/5. Rewrite it. The inverse function of x is 1/5 x minus 6/5. Which is that? And you're going, how is it that? Ours doesn't look like that. Back here, when we had x minus 6 equals 5y, they just did this. Instead of doing it, breaking it all down, they just left it x minus 6 over 5 because neither of them would go evenly. So you can also write your inverse as x minus 6 over 5. Your domain, even though they didn't ask for it, there's no drama in the function. There's no drama in the inverse. Your domain would be negative infinity to infinity. And if I graph them, again, there's my two lines. There's mother. They all intersect in the same spot. Telltale sign that you have inverse functions. Alright, they're going to get a little more complicated. They want me to find the equation for the inverse if the function is x over x plus 1. This gets a little more complicated, but it's kind of fun. So switch to y equal x over x plus 1. Switch your x and y, all of them. Every y is an x, every x is a y. Now we got to get y alone. Well, I've got two y's, one on top, one on bottom. I don't like fractions. I got to get rid of the fractions, so I'm going to multiply by the denominator, because multiplying by something you're dividing cancels out. And now over here, if I distribute, I get xy plus x equals y. I still have two y's, and they're on opposite sides, so I'm going to get them on the same side. So I'm going to minus xy. That gives me x equals y minus xy. Well, now that I have them on the same side, I can factor y out. If I factor out y, I get 1 minus x. And now I can get y alone if I divide by 1 minus x on both sides. Which means my inverse function is x over 1 minus x. Okay? Now I have drama. Okay? This says that Mr. Denominator, you may never equal 0. So minus 1 minus 1, negative x may never equal negative 1. Divide by negative 1, and x may never equal 1. Okay? So if that's my restriction, then my domain is everything else, which would be negative infinity to 1, union 1 to infinity. Alrighty? Sorry, I forgot I did that again. Alright, and look, if I graph them, if I type in x divided by x plus 1 and x divided by 1 minus x, and I graph them, you can see when you graph the x over x plus 1, I'm trying to think. I think you get these two boomerangs. And then when you graph the x over 1 minus x, I think you get these, I don't know, somehow you get those two. But notice that mother intersects both of those, and in other words, you can tell that they're symmetric about mother. Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got 1. Alright, change to y, and then switch x and y. So that's going to be x equals negative 3y minus 7 over 9y minus 4. Kill the fraction. I'm going to multiply both sides by the denominator. Distribute the x. I get 9xy minus 4x equals negative 3y minus 7. I want to get my y's on one side and everything without a y on the other. So I'm going to do two things at once. I want my y's together, so I'm going to add 3y to this side. I don't want that x term. So I'm going to add 4x to both sides, and that gets rid of that on this side. So what I end up with is 9xy plus 3y equals negative 7 plus 4x. And now I have both terms with y on it, so I can factor out a y, which leaves 9x plus 3 equals negative 7 plus, and they're going to write it 4x minus 7, because it's just more proper that way. And now, to get y alone, I'm going to divide by 9x plus 3. So my inverse function is 4x minus 7 over 9x plus 3. My domain, Mr. Denominator, you may never equal 0. So 9x may never equal negative 3. Divide by 9. X may never equal negative 1/3. So my domain would be negative infinity to negative 1/3 union negative 1/3 to infinity. Okay? And if you look at the graph, there you go. Alright, let's find the inverse of a cubic function. Switch to y. 2x cubed minus 5. Change x and y, so that's x equals 2y cubed minus 5. Get y alone, add 5, I get x plus 5 equals 2y cubed. Divide by 2. And I get x plus 5 over 2 equals y cubed. Kill the cube with a cube root. And I get the inverse function of x is the cube root of x plus 5 over 2. And there's no drama. I do have a radical, but that's odd, so odds aren't going to affect anything. So my domain would be negative infinity to infinity. Okay. And oh yeah, I wanted you to see these. Here's my function, and here's my inverse function that I typed into y equal. And if you look at the graph, there's one of them, there's the other one, there's mama, and they all intersect in the same spot. Alright, try this one, hit pause, come back when you're ready. And hopefully you got 3. So I'm going to switch to y. Then I'm going to switch x and y. So x equals 2y cubed plus 7. Then I'm going to get y alone. So minus 7. I get x minus 7 equals 2y cubed. Divide by 2. I get x minus 7 over 2 equals y cubed. Kill the cube with a cube root. And my inverse function of x is the cube root of x minus 7 over 2. Yeah, and again, there would be no drama. Cube roots don't cause drama, just even roots do. So the domain would be negative infinity to infinity. Alright, and if I graph these, again, 1 cubic, 2 cubic, mother, all intersect in the same spot. Alright, let's try this one. And I forgot to animate the graphs. Alright. Switch to y. Then change x and y. So x equals the cube root of y plus 9. And then get y alone. Well, I got to get them out from the radicals. So to get rid of a cube root, I'm going to cube, but I got to do it to both sides. So I get x cubed equals y plus 9. Minus 9 minus 9, I get the inverse function of x equals x cubed minus 9. So I typed in the cube root of x plus 9 and x cubed minus 9, and again, 1 cubic, 2 cubic, mother right in the middle. Okay. Alright, you try this one, hit pause, come back when you're ready. And you should get 1. Alright, switch to y, change x and y, so x equals the cube root of y divided by 8 minus 4. Get y alone, I gotta add 4 first. That gives me x plus 4 equals the cube root of y over 8. To kill a cube root, I'm going to cube both sides. And I'm not going to actually multiply it out, I'm just going to leave it like that, equals y over 8. So to get rid of the divide by 8, I'm going to multiply by 8, and I get the inverse function of x is 8 times x plus 4 cubed. Okay? And again, if you look at those, 1 cubic, 2 cubic, mother in the middle. Alright, so how do you find the inverse of a function and determine its domain? Well, 1, you change f of x to y. 2, switch x and y. 3, get y alone. And 4, rewrite it using that instead of y. Alright, how to determine whether a function is one-to-one. We already talked about that if it passes the vertical and horizontal line test. How to graph the inverse of a function from a graph, not an equation. You have 2 methods. You can do the mirror method, which says draw mother, the identity, y equal 1x, and whatever's happening up here, you just mimic it and you replace it over here. Basically reflect it over. Or you could make a table of values, a table of ordered pairs, switch your x and y, regraph those, and you'll also have your inverse. Alright, so if I look at this one, oh, here it's showing you. Okay, so here's the graph of f. It draws mother, okay, the mirror, y equal x, and then it basically reflects this over. This technique does not work well for me because I can't see reflections very well. Like mine are always jacked up. The guy who was trying to draw it and go, oh, which I kind of did right. Normally I'm not that good at it. Alright? And so there would be the graph of your inverse. Alright. So let's do this using, it's the same one they just gave me. I'm going to do it using a table of values. And what you can do is you can find these points on here. Make an XY table. That ordered pair right there, I'm going to say is about -2, -4. Then I picked this point and I got -1, 0. Then I picked that point and I got -0.5, comma, I know it doesn't look like it's at -0.5. What did I do? Yeah, it is. -0.5, comma 1. And then I picked another point right here, which I'm a little far off, but I'm going to go with 0.5, comma 1. And it's a little bit above, so I'm going to go 1.1. Okay. And then I picked another point, and I got 2, 4. So all you do to use the second technique is you switch your ordered pairs. So this now becomes -4, -2. This becomes 0, -1. This becomes 1, -0.5. This becomes 1.1, 0.5. And this becomes 4, 2. And if I plot these points, -4, 2. I know I drew a nice pretty graph over here, but -4, 2. 0, -1. 1, -0.5. 1.1 is 0.5. And 4 is 2. So if I draw this, except for that's -4, -2, schmo. So if I draw this, it's going to go, and this is where I have a hard time. And again, picture mother in there, and it's got to reflect over that. Okay? Alright. So let's determine if this is 1-to-1. It passes the vertical, but it does not pass the horizontal. So it's not 1-to-1, which means we don't have to graph its inverse. So not 1-to-1. Alright. I could find points and all of that, but you don't have to. Okay, find this one, hit pause. You can do the points, you can do the mirror method. In a multiple choice situation, remember what I told you, all the graphs have to look like if they're inverses. And hopefully you got this one. You can tell, guys, look, here's their first, and here's what they're claiming is their inverse. Does mother intersect where they do? No. This one, there's that, and they're claiming this is the inverse. No. Look at this one. Bloop, bloop. Look at mother. Intersects right where they do. It's got to be 3. I mean, you can do the math if you want to, but if in a multiple choice situation, look for the graph that has that reflection property. Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got A. Again, you can do the math if you want, but if I look and I add my mother functions in, the only one where the mother and the two functions intersect in the same spot is A, so it's got to be A. Alright, so how do you find the inverse of a non-invertible function by restricting its domain? Look at the part of the graph that makes the inverse not pass the vertical line test and restrict the domain or range so that the function will pass. An easy way pretty much is, this is a function, but if I do its inverse, it's not. But if I only look at the positive part, in other words, if I only look at the positive, the part of the graph where x is positive, I would get this. Okay? That does pass the vertical and the horizontal. So if I just restricted this and said x has to stay greater than or equal to 0, look what happens. Okay? I got y squared equals x, which means y equals plus or minus the square root of x. Okay? The inverse is not a function. But if I do y equals the square root of x, just positive x, I just get this top part, which means it will pass. Okay? And I can make the inverse, which would be this. Okay? No, this would be the inverse. This would be the restricted one. Alright. So, how do you find the invertible? Pretty much restrict your domain. Restrict to keep x positive. That usually works. You gotta get a little creative sometimes. Alright, so we are at homework, which means we are done. Happy homeworking. And I will see you next time.